Good evening, students. Welcome to our class. In today's lecture, we are going to discuss about the problems on a photoelectric effect and Compton effect. As we know, the photoelectric effect occurs when light above a certain frequency or threshold frequency is fall on a metal like a zinc. This causes electrons to escape from that metal. The escaping electrons are called as photoelectron, and it carries a current, that is photoelectric current, and this overall effect is called as photoelectric effect. The frequency of the light need to reach a particular minimum value for photoelectrons to start escape from the metal. The photoelectric equation involved is in this effect is Hf is equal to phi plus Ek, where H is a Planck's constant, F is the frequency of incident light, phi is the work function, Ek is the maximum kinetic energy of the emitted electron. Similarly, as in Compton effect, we can find out, we derived Compton shift equation, that is lambda prime minus lambda is equal to h by m naught c into 1 minus cos theta. H by m naught c is nothing but a Compton wavelength, and lambda prime minus lambda is nothing but a delta lambda, which is called as a Compton shift. And in today's lecture, we are going to discuss some numerical problems related with the photoelectric effect and Compton effect. Let's see. In first problem, the work function of barium and tungsten is 2.5 electron volt and 4.2 electron volt respectively. Check whether these materials are useful in a photocell which is to be used to detect a visible light. Solution for this problem is that the wavelength lambda of visible light ranges from 4000 to a 7000 angstrom. We are able to see within a range of 4000 to 7000 angstrom only a Wijnor spectra, violet to a red wavelength. The energy for 4000 angstrom wavelength is equal to hc by lambda, which is equal to, we know the Planck's constant, we know the velocity of light, and lambda is 4000 angstrom. If we simplify, it gives 3.106 electron volt. Energy for 4000 angstrom is 3.1 electron volt. Similarly, energy for 7000 angstrom is 6.62 into 10 to the power of minus 34 into 3 into 10 to the power of 8 divided by 7000 angstrom into 1.6 into 10 to the power of minus 19, because we are going to convert this energy in terms of electrovolt. For that, we are dividing with a charge of an electron. If we simplify that numerical calculation, we will get 1.77 electron volt. If we see energy required for 4000 and energy required for 7000 is 1.77 and 3.106 respectively, and the work function for the barium is 2.5 electron volt and tungsten is 4.2 electron volt. Means the work function of tungsten is 4.2 electron volt, which is more than the energy range of visible light. Means we cannot use a tungsten. Hence, barium is the only material useful for detecting a visible light. In this way, we can find out which material is useful to detect a visible light. In second numerical, light of wavelength 2000 angstroms fall on a metal surface if the work function of the surface is 4.2 electron volt, phi is 4.2 electron volt. What is the kinetic energy of the fastest photoelectrons emitted? Also calculate stopping potential and the threshold wavelength for the metal. First of all, we want to find out the energy associated with the wavelength 2000 angstrom, which is equal to hc by lambda. If we substitute the value of h, c and lambda, we will get energy for radiation having wavelength 2000 angstrom is 6.212 electron volt. Work function phi is equal to 4.2 electron volt. Now kinetic energy for fast moving electron is the difference between energy of radiating wavelength 2000 angstrom is 6.212 electron volt minus work function 4.2, which is equal to 2.012. This much is stopping potential, which is equal to 2.012 electron volt. Now I want to find out the threshold wavelength. Lambda 0 is equal to hc by work function. hc by work function. In this way we can find out the threshold wavelength. We know the value of Planck's constant, velocity of light. Work function is 4.2 electron volt. We have to convert into joule per, or we are going to convert into Armstrong. That's why we have to divide with charge of an electron, 1.6 into 10 to the power of minus 19 joule per electron volt. If we simplify, then lambda naught is equal to 2958 Armstrong. This is a threshold wavelength, 2958 Armstrong. Means we can use our photoelectric concept in a two different way. And work function W is equal to minus EF minus E phi minus EF, or phi is equal to HF minus EK, in both way. In third problem, what is the work function of a metal if the threshold wavelength for it is 580 nanometer? If light of 475 nanometer wavelength falls on a metal, what is its stopping potential? Work function phi is equal to hc by threshold wavelength. They providing threshold wavelength which is equal to 580 nanometer. If we substitute that value, then work function is 2.14 electron volt. Next, energy for 475 nanometer is hc by lambda. If we substitute the value of h, c and lambda, then energy for 475 nanometer radiations is 2.62 electron volt, and stopping potential is nothing but a difference between the energy and work function, 2.62 minus 2.14, which is equal to 0.48. This much stopping potential of that metal. Next, a photon of wavelength 4 Armstrong strikes an electron at rest and its scattered angle of 150 Armstrong to its original direction. Find the wavelength of a photon after collision. For this, we have to use a compensative formula, which is equal to lambda prime minus lambda is equal to h by m naught c into 1 minus cos phi. Here the phi is 150 degrees. If we substitute that value, then h by m naught c into 1 minus cos 150 degree, 6.626 into 10 to the power of minus 34 joule second into 1 minus cos 150 is 1.866 divided by m naught. The rest mass of a photon is 9.1 into 10 to the power minus 31 10 to the power of minus 31 kg into 3 into 10 to the power of 8 meter per second. If we simplify, then change in wavelength or Compton shift is 0.045 angstrom. In this case, I want to find out the wavelength of a photon after collision, that is lambda prime. Lambda prime is equal to lambda plus Compton shift. We know the value of lambda is 4 plus 0.045 angstrom, which is equal to 4.045 angstrom. Then wavelength of photon is 4.045 angstrom. Next, when the radiations of wavelength 1500 angstrom in incident on a photocell, electrons are emitted. If the stopping potential is 4.4 volt, calculate the work function, threshold frequency and threshold wavelength. Such kind of problems we will ask for a 5 mark also. Energy of incident photon is hc by lambda. We know the wavelength. By using that wavelength, we can find out the energy of incident photon is 8.28 electron volt. Now, next I want to find out the work function. Work function is nothing but the energy of incident photon minus stopping potential. 8.28 minus 4.4 is, it gives 3.88 electron volt. Once you will get work function, you can find out threshold frequency or threshold wavelength, which is equal to C by nu naught, or nu naught is equal to 3.88 into charge of an electron 1.6 into 10 to the power minus 19 divided by Planck's constant 6.62 into 10 to the power of minus 34. E by h only, simply E by h, which is equal to 9.4 into 10 to the power of 14 hertz. If we use that threshold frequency to find out threshold wavelength, lambda is 0 is equal to C by nu naught. We know the value of C is 3 into 10 to the power of 8 meter per second divided by 9.4 into 10 to the power of 14 second. It gives 3191 angstrom. 3191 angstrom. If a photon has a wavelength equal to the Compton wavelength, next numeric. If a photon has a wavelength equal to the Compton wavelength of the particle, shows that the photon's energy is equal to the rest energy of a particle. Then Compton wavelength of a particle is h by m naught c. H by m naught c. Wavelength of a photon having energy E is equal to h, having energy E is equal to hc by E. Both are wavelength. If we compare that h by m naught c is equal to hc by E, it gives E is equal to m naught c square, which is a rest energy of the particle. In this way, we can show that the rest energy of the particle E is equal to m naught c square. Next, if X-ray of wavelength 1.5 angstrom are scattered from a block of carbon, what will be the wavelength of scattered X-rays for angle 180 degree, 90 degree and 0 degree? As we know, lambda prime is equal to lambda plus h by, or lambda prime minus lambda is equal to h by m naught c into 1 minus cos phi, or lambda is equal to lambda prime is equal to lambda plus h by m naught c 1 minus cos phi. If lambda is equal to 1.4 angstrom, then my aim is to find out h by m naught c into 1 minus cos phi. H by m naught c into 1 minus cos phi. H by m naught c is nothing but a Compton wavelength, which is equal to 0.024 Armstrong. 0.024 Armstrong. First of all, we want to find out h by m naught c. Then if we substitute that value, lambda is equal to lambda plus h by m naught c into cos 180 degree 1 minus cos 180. Cos 180 is equal to minus 1. 1 minus 1 is plus 1. 1 plus 1 is 2. We know the value of Compton wavelength h by m naught c is equal to 0.024. If you substitute that value, then lambda prime is equal to 1.45 Armstrong. Similarly, for 90 degree, cos 90 is 0. Therefore, lambda prime is equal to lambda plus h by m naught c, which is equal to 1.42 Armstrong. In second case, cos phi is equal to 1, cos phi is equal to 0, cos phi is equal to 0, cos phi is equal to 1. 1 minus 1 is 0. Therefore, lambda prime is equal to lambda plus h m by m naught c into 1 minus 1 is equal to 1.4 Armstrong. Means wavelength of scattered X-ray is different for a different angle. For 180 degree it is 1.4 Armstrong, for 90 degree it is 1.42 Armstrong, for 0 degree it is 1.4 Armstrong. This is all about the numerical problems related with the photoelectric effect and Compton effect. In next lecture we discuss about the Pauli's exclusive principle and their applications. After that point, we will end with first chapter, and after that we will discuss some numerical related with group velocity and phase velocity. Okay. Thank you.